In the previous video, we discussed how to define momentum and impulse so that we can get a new formulation of the Newton's second law. Now, in this video, we'll talk about some cases where it's hard to apply Newton's second law, and application of the impulse momentum theorem is easier. Application of impulse momentum theorem. Now, the first example I want to show you is the a tennis ball hitting the net of a racket. Tennis ball hitting, here is the racket. Let me draw a schematic picture to represent these two objects. Okay, so here's the net of the racket. Okay, now we have a tennis ball flies in with some initial velocity. Let's call this vi before it hit the net. Okay, and while the ball is hitting the net, the net, of course, will have some deformation, right? So it will be pushed. The net will be pushed this way, and then here's the instant where we have the ball. The instant the ball is right on the net of the racket. Some deformation. Trying to draw some deformation of the net, the strings on the racket. Okay. All right. So let's talk about this process. Okay, and the strings on the racket, of course, will apply a force on this tennis ball. Okay. So our focus is, or our system is, tennis ball, and we are studying the force acting on the tennis ball. Okay, now in this case we're going to neglect the gravity. Gravity, of course, is still there. It's just that compared to the force due to the net, right, acting on the ball, this force, the gravity is small, so we can neglect it. Okay. Now we know that the racket is like, their strings are like springs, right? So when you stretch them, they can give a reaction, so that there's a reacting force, right, on the tennis ball. So at this instant, let me draw the force. And that force is due to the string, okay? Kind of like spring force, okay? And the more the deformation of the net of the racket, the larger the force. So this force, okay, so it's by the racket on the ball. Okay, changes with time. So it's a function of time. And this time can also be translated into the deformation of the string. Right, the more deformation, the larger the force. So in principle, we can draw a picture for such a force. And it turns out to be this kind of diagram. So it's a bell-shaped. It's a bell-shaped curve that started from 0, representing the initial time instant when the tennis ball just touched the net, just touched the string, until the maximum deformation somewhere here. And then later on, when the string tries to return to its original length, the ball is being pushed backward, and then that will correspond to the other side of the bell shape. Okay, so the shape here is it's a bell-shaped force versus time diagram. Okay, so the force here you can see is changing all the time throughout the process. And here's the 0 force at the beginning. Okay, let's call this Ti, and that'll be the T final. Okay, and this line here, right, is right in the middle, represent maximum deformation or maximum distortion. Maximum distortion of the string. Okay, and here the force is max, so that's F max. Okay, so now we see in this case here, the force is changing with time, so it's very hard to apply Newton's second law, because we don't actually know exactly this kind of curve, right? The curve here. Okay, all right. So now think about the same problem, but from the momentum change point of view. So if I think about, let's say, afterward, here is again a racket, okay, and its net is going to, all these strings going to go back to the original shape. Okay, now you guessed what I'm going to say, right? So the tennis ball now flies out with a final velocity. Okay. Now in this case, these two velocities, they will correspond to this initial instant and final instant. Okay. So how about we think about the process here, not care about when we do not care about the intermediate process, this force changing with time process. Instead, we think about the initial and final momentum, and if we can figure that out, then we can say we solve the problem. Okay, so let's think about how about just talk about delta P, which is mass of the tennis ball times the velocity change, and then we get this final velocity from initial velocity plus delta P over M. So I simply just rearrange these M times Vi term, rearrange it to the left side, and then it will be added up. It has summation with delta P, and then we divide by M. Okay, and then we figure out the final velocity. So that's the something we care about, right? So we want this, and we know Vi. Okay, so the question is, do we know delta P over M? So what's this, right? What's this? So the answer is from momentum impulse theorem, because it says that delta P equals J. Okay, and J is defined as the string's force integral from initial to final time. Okay, so if we know that, then we should be able to do this calculation of the V final, and that integral is the area under the curve. Okay, so let me draw this area, and that's this shaded area. And in a lot of situations, we can actually calculate this area. Okay, suppose we know it's bell shape, and we could have some Gaussian function to imitate this bell shape. So that's just one example. Okay, so Gaussian function, and we can do this integral, right, of the area. Okay, then we can calculate the delta P or J, and then we can figure out the V final. Okay, so that's just one general discussion of how we can apply this impulse momentum theorem to a process that look like this. Now, another process I want to address here is called a collision process. And in such a process, of course, the let's say these two objects collide. Object A collide with object B, and that is called the collision process. Okay, so in the process, of course, the force between the two objects, they changing with time. Okay, so collision also has a variable force, varying force, sorry. Force is a function of time. Not only that, but also it happened very quickly. So the process that's called the delta T, the time interval here, is in the order of millisecond. So in the order of millisecond, and then it happens very quickly. And we'll see later on that this one is the important condition for neglecting some other forces, some external forces in the process. Okay, so these are the two properties of collision process, and then we're going to say that in such a process, we can apply impulse momentum theorem in the sense that we can neglect this impulse, okay, this net impulse. We can say that it's almost a zero, and then we have delta P equals 0, which means P final equals P initial. Okay, and that is called momentum conservation. So in the collision process where two objects collide, it happens very quickly, and then due to that condition, we can say that's momentum conservation. Okay, so I said that the net torque on the object equals 0. This net torque refers to net torque due to external forces. The interaction between A and B does not count as external force. Let's look at one picture here. Now, when they collide, I'm going to draw that collision instant. we have A and B touching each other, and there's a normal force, of course, between them. There's normal force B acting on A, and there's normal force A acting on B. Okay, so these two forces are their action reactions, and they're equal in magnitude, right? So that's something we already know. But we're going to say that these two forces, they are internal. They're internal forces. So they do not go in the calculation of the net torque. If we say our system is A plus B, okay? So our system is not A or B, it's A and B together, right? They together, right, is called our system. So that will make the normal force between the internal forces. So do not consider them here, okay? So external forces in this example here. So now let's say they collide on a horizontal surface. On a horizontal surface. Then in order to have this condition, we would say let's say when they collide, there are some frictions, right, acting on them. So the friction force are negligible. So in this case here, I'm going to draw, let's say, when they are colliding, they're still sliding on the surface, right? So that's Fk here acting on A, Fk here acting on B, okay? So we're going to say these two forces are almost zero, okay? In the sense that these frictions they're much smaller, much smaller than the normal force, okay, in that sense. So that's how we can neglect them. Okay, if you think about the collision process, it also happens very quickly. So the impulse, we can further reduce the effect of these two frictions by looking at the impulse they deliver to the system. Okay, so the impulse due to Fka, so approximately Ka delta T, and due to this small scale of the time, that's almost zero. And similarly for the impulse for B. So that's how we can neglect it. Okay. Now some other situations. Before I talk about other situations, so you may say there's also this normal force on A, normal force on B, and then there's gravity A, gravity B. Okay, so I'm going to say that in this case here, because of the support of the horizontal surface, these two pair of forces, they cancel each other. So if I think about the object A, normal force plus gravity, these two vectors must be zero, right? Because they're in opposite directions. And similarly for B, and that's why their collective contribution to the torque will be zero. So the torque due to, their collective impulse, normal force plus gravity, will be zero. They will cancel out, okay? So this net impulse here becomes zero. So that's why we can neglect them. Now let's talk about one case where we don't have these cancellation, and then see how we can argue that the collision process conserves the momentum. Okay, so it's a collision in mid-air. Okay, so let's say there's this object A collide with object B in mid-air. Okay, so why can we neglect external forces such as the gravity, MAG, MBG? Okay, so we're in the process of collision. These two forces are still acting on the A and B, right? So also the external. So we should account for that contribution for the impulse. J due to gravity, right, is given by, for the whole system, the total gravity here times delta T. Okay, so that kind of impulse will be delivered to the change of the total momentum of the system. So the system here is A plus B. So think about the total momentum change for both A and B. Okay. Now we're going to use the argument that we talked about in the earlier slide. We're going to talk about this delta T here. Okay, because it happened very quickly. Even if it's in mid-air, this delta T is in the scale of millisecond. Okay. Now the normal force between these two objects, we can say, during the collision, is much larger than the gravity. So that's why either from the scale of the force, the magnitude of the force, but also the time scale here, right, the delta T scale here, we can say we can neglect. Okay, so we in the future going to neglect this impulse due to the gravity. So that's the collision process. Okay, so now I'm going to talk about different types of collision. And then what's the property of these types of collisions? Okay. Now for all collisions, we know their momentum, total momentum, is always conserved. So let's say there's a collision between A and B. Okay. So first property, momentum, total momentum of A and B is always a constant. That is always conserved, right? Momentum is always conserved. Now the second property is the basis of dividing the collision process into different types. Okay, so the second property that I'm going to discuss here is the energy, mechanical energy. So we talk about this mechanical energy in a different chapter. So if you're not familiar about this mechanical energy definition, I would suggest you go there first and then return here to think about the energy description of the collisions. Okay, so the mechanical energy symbol is E, and is defined as K plus U. Okay, so here's mechanical energy. Now K here is called a kinetic energy, and U here is called a potential energy. Okay. All right, so that's kind of like a simple definition of this energy that we're looking at. And kinetic energy is defined as 1/2 v squared. Okay, so it's related to the mass and the velocity squared of this object. And potential energy here, we're going to just consider the potential energy due to the gravity. Okay, so that's mg times the y position. Okay, so we're going to build a coordinate system: x horizontal, y vertical. And if an object with mass m is at a coordinate of y in such a system, and we regard the y equals 0 level as 0 potential level, then we have mgy as the potential energy of this object. Okay, so that's like a quick definition of various quantities. Okay, so with that definition, the second criteria here that we're going to use to divide the collisions into different processes, different types, is that based on the energy conservation here. Now, if before the collision we call this EI equals final mechanical of the system, then we say this kind of collision is elastic collision. Okay, now if the energy is lost, the part of the energy is lost, so EI is greater than E final. Okay, then I'm going to say this kind of collision is inelastic collision. And inside this inelastic collision, we also have two different categories. One is simply just inelastic, called inelastic, and the other one is called completely inelastic. So what's the difference between these two? Let's look at one example. Let's say there are two objects here colliding. Okay, now after the collision, so that's before, let's call this I state, and after the collision they stick together. So that's this VA and VB. Now after the collision they move together with a common velocity. Let's call this VC. Okay, so that's final state. So here is common velocity. Okay, meaning they stick together and then move together, and that is called completely inelastic. That's the definition of this. Okay, now inelastic collision will be after the collision, A maybe go that way, VA final, and B maybe go this way with VB final. Okay, so they have two different velocities. They will separate. Okay, that's called an inelastic collision. But nonetheless, they still lose energy. Okay, so in this case here, there's still less final mechanical energy compared to the initial mechanical energy. Now, there's another category of the collision process. In that process, initial energy is less than the final energy. So the mechanical energy of the system increases, right, during the collision process. And this process are also called explosion. Okay, so what kind of process gives us this? So let's say originally A and B, they're together. They move with some velocity, some common velocity. And then later on they explode. And then break up into two different pieces. VA final and VB final. That's in the final state. Okay. Now, of course, we don't actually need this VC here. So now let's say there's an object at rest at a location, right? And then it suddenly explode. That's also our case here. Okay. Now, where do we have this extra energy, right? Where do this energy come from? The energy comes from other types of energy, not mechanical energy, some chemical energy. For example, okay, so in an explosion process, chemical energy becomes the mechanical energy of the system. So there's still energy conservation. It's just that mechanical energy is not conserved. Right? Other type of energy is converted into the mechanical energy. So that's called different types of collisions. Okay, and I hope that help your conceptual understanding of the collision process. And next time we're going to talk about how to apply momentum conservation to study this collision process. Okay, so again, as I said, that the total momentum of a system is always conserved. Okay, so we don't need to worry about whether we can apply this momentum conservation or not to collision process. In such a process, total momentum is always conserved. Okay, and we don't care about the energy conservation right now. But in some other cases, when we want to do more calculations, then we will talk about the energy. Okay, and we'll see that in the next video. Thanks for watching.